Hello there, and welcome to Get Sleepy Science. I'm so grateful you found your way here tonight. Far beyond our world, in the vast darkness between stars, something extraordinary is passing through. Tonight, we'll drift gently through the story of 3I Atlas, the third visitor from interstellar space ever discovered. A wanderer from another star system, carrying secrets from a place we may never visit, now traveling through our small corner of the cosmos. Wherever you are right now, perhaps lying in the quiet darkness of your bedroom, or perhaps with a window showing the night sky above, allow yourself to settle into this shared moment of stillness. Tonight, explore 100 remarkable truths about this interstellar comet. From the moment astronomers first spotted its faint light, to the telescopes around the world that tracked its journey, to the ancient ice and dust that make up its core, revealing stories from a distant solar system we can only imagine. If this quiet exploration of the cosmos helps you unwind, a gentle like and subscribe helps other stargazers find their way here too. It only takes a moment, but it means the universe to us. One sleepy soul at a time. For now, you don't need to do anything at all. Just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself floating in a spacecraft, far from Earth, watching this ancient comet drift past your window. A traveler from another star, on a journey that began long before you or I were born. Now, if you're ready, let's begin our quiet journey through the mysteries of 3I Atlas. Now, if you'd like, close your eyes and take a deep breath. Imagine you're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through infinite space, and when you're ready, begin. On July 1st, 2025, astronomers using a telescope in Chile detected something unusual moving across the night sky. The asteroid terrestrial impact, last alert system, known as ATLAS, had found a faint object that didn't move like the asteroids and comets that belong to our solar system. Within hours, observatories around the world were turning their telescopes toward this mysterious visitor. Pre-discovery images showed it had been moving through our solar system since mid-June, passing in front of the dense star fields of the Milky Way's center, which is why it had been so difficult to spot earlier. By July 2nd, astronomers had collected enough observations to confirm what they suspected. This was no ordinary object. It was moving too fast to be bound by the sun's gravity. It came from somewhere else. This was only the third interstellar object ever discovered passing through our solar system. Scientists named it 3I Atlas, where the 3 means third. The I means interstellar, and Atlas honors the telescope that found it. A visitor from beyond, caught in the act of passing through. When astronomers first spotted 3I Atlas, it was about 410 million miles from the Sun, roughly the distance where Jupiter orbits. At that moment, the comet was traveling at approximately 137,000 miles per hour, or about 61 kilometers per second. To put that in perspective, that's more than 180 times faster than a commercial airplane. This incredible speed told astronomers something important. Objects that belong to our solar system travel at speeds that allow the sun's gravity to hold them in orbit, bringing them back again and again. But 3I Atlas was moving far too quickly for that. The sun's gravity would bend its path slightly as it passed, but it would never capture the comet. It would never return. This speed meant only one thing. 3I Atlas had come from interstellar space, the vast region between stars, where our sun's influence fades to almost nothing. A true wanderer, visiting once, then continuing on into the cosmic dark. The trajectory of 3I Atlas follows what astronomers call a highly hyperbolic orbit. Unlike the elliptical orbits of planets and comets that belong to our solar system, which loop back around the sun in closed paths, a hyperbola is an open curve. It comes from infinity and returns to infinity. The mathematical measure of this shape is called eccentricity. Any orbit with an eccentricity greater than 1 is unbound, meaning it will never close. Early calculations showed that 3I Atlas has a very high eccentricity, indicating it's moving much faster relative to the Sun than typical solar system objects. For comparison, the first interstellar visitor, Oumuamua, had an eccentricity of about 1.2, and the second visitor, 2I Borisov, had an eccentricity of 3.6. The extreme speed of 3I Atlas confirms its interstellar origin beyond any doubt. It's not just visiting, it's racing through. Unlike the first two interstellar visitors, 3I Atlas arrived from an unexpected direction. It came from the southern celestial hemisphere, moving in a direction roughly opposite to the solar apex. The solar apex is the point in the sky toward which our sun is moving relative to nearby stars. Astronomers had predicted that most interstellar objects would come from that direction, carried along by the general flow of stellar motion in our region of the galaxy. But 3I Atlas surprised them. It came from the south, moving retrograde, which means it's traveling in the opposite direction to most objects in our solar system. Its orbital plane is inclined at just 5 degrees relative to the ecliptic, the flat plane where most planets orbit. This nearly flat trajectory, combined with its southern origin, suggests that either 3I Atlas is a rare discovery, or perhaps southern origin. Interstellar objects are more common than scientists initially thought. The universe, as always, refuses to fit neatly into our predictions. Within days of its discovery, astronomers confirmed that 3I Atlas is not an asteroid, but a comet. The distinction matters. Asteroids are rocky bodies, remnants of planetary formation that never gathered enough material to become planets. Comets, by contrast, are mixtures of ice, dust, and rock, often described as dirty snowballs. On July 2nd, 2025, multiple observatories, including the Lowell Discovery Telescope in Arizona, the Canada-France-Hawaii Telescope at Mauna Kea, and the Deep Random Survey in Chile, all reported seeing a fuzzy cloud around the object. This cloud, called a coma, forms when solar radiation heats the comet's frozen surface, causing ice to sublimate directly from solid to gas. The gas and dust released create a glowing halo that can stretch thousands of miles into space. Later observations by astronomers David Jewett and Jane Liu confirmed that 3I Atlas was clearly active, with a diffuse appearance characteristic of comets. This activity meant scientists could study not just the comet's motion, but also its composition, learning about the chemistry of a distant star system from the gases being released into space. Using NASA's Hubble Space Telescope, astronomers captured detailed images of 3I Atlas on July 21, 2025, when the comet was about 277 million miles from Earth. Hubble revealed a teardrop-shaped cocoon of dust streaming away from the comet's solid, icy nucleus. Because Hubble was tracking the moving comet, the background stars appeared as streaks in the long exposure photographs, while the comet itself remained in sharp focus. These images allowed scientists to estimate the size of the comet's nucleus more accurately. From Hubble observations, by mid-August, astronomers determined that the nucleus is no smaller than 1,444 feet in diameter, which is roughly the height of the Empire State Building. However, it could be significantly larger, possibly as much as 3.5 miles across. The uncertainty comes from the brightness of the coma, which makes it difficult to see the nucleus clearly. Still, this range of sizes tells us something important. Even on the smaller end, 3I Atlas is large enough to have survived a journey of millions or billions of years through the harsh radiation and impacts of interstellar space. In late July and August 2025, astronomers using NASA's Neil Gehrels Swift Observatory made a surprising discovery. They detected hydroxyl gas, marked by the chemical symbol OH, glowing faintly in the ultraviolet light around 3I Atlas. Hydroxyl is a chemical fingerprint of water. When sunlight strikes water molecules in a comet's coma, it breaks them apart, creating hydroxyl among other byproducts. What made this detection surprising was the distance. The comet was nearly 3.88 astronomical units from the Sun, almost 4 times Earth's distance, where temperatures remain extremely cold. Most comets don't release significant amounts of water at such distances because the sunlight is too weak to sublimate much ice. Yet 3I Atlas was actively producing water vapor far from the Sun. This suggests something unusual about its structure. Perhaps sunlight was heating small icy grains released from the nucleus, allowing them to vaporize gradually. Or perhaps the comet contains complex, layered ices that preserve volatile materials more effectively than typical solar system comets. Each interstellar visitor reveals different chemistry, like notes from distant laboratories we can never visit. A team of researchers using the Very Large Telescope in Chile detected something even more unexpected in the spectrum of light coming from 3I Atlas. They found glowing nickel vapor in the comet's coma. This discovery was made on July 20th, 2025, when the comet was still 3.88 astronomical units from the Sun. Nickel is a metal, and metals typically require high temperatures to vaporize. At the distance where 3I Atlas was located, temperatures should have been far too cold for nickel to turn into gas. Yet there it was, unmistakably present in the spectral data. The detection was made using spectrographs called X-shooter and UVES, which break light into its component wavelengths, like a prism, allowing scientists to identify specific elements by their unique spectral signatures. Over multiple observation sessions, The team found that levels of nickel vapor continued to increase as the comet moved closer to the Sun. This nickel detection at such unusual distances suggests either that the comet's interior structure is releasing metals through some complex process, or that impact events in its distant past enriched its surface with metallic materials. The chemical signatures reflect both the comet's ancient origins and its long journey through the darkness between stars. The composition of 3I Atlas tells a story about where it might have formed billions of years ago in another star system. The presence of water ice, carbon compounds, and metals like nickel suggests it formed in a region with similar conditions to the outer parts of our own solar system. Comets in our solar system typically form in the cold outer regions beyond the orbits of Neptune and Pluto, where temperatures are low enough for water and other volatile compounds to freeze. When planetary systems form around young stars, gravitational interactions between growing planets can fling some of these icy bodies outward. Some escape entirely, becoming wanderers in interstellar space. 3I Atlas may be one of these exiled objects, kicked out of its home system, millions or even billions of years ago during the chaotic early period of planetary formation. Its chemistry may reflect the conditions of that distant stellar nursery, preserving information about star and planet formation processes that we can only study indirectly. Every molecule detected, every element identified, is a clue to understanding not just one comet, but the diversity of planetary systems throughout the galaxy. As 3I Atlas traveled through our solar system, NASA coordinated an unprecedented observational campaign involving multiple spacecraft. This wasn't planned in advance. Interstellar objects are too rare and unpredictable for that. Instead, mission teams quickly adjusted their schedules to capture data on this once-in-a-lifetime visitor. The James Webb Space Telescope, the most powerful space telescope ever built, turned its infrared instruments toward the comet. The Hubble Space Telescope continued its optical observations. The Neil Gehrels Swift Observatory monitored ultraviolet emissions. Even NASA's Psyche spacecraft, traveling to study a metal-rich asteroid, took observations during its closest approach to 3I Atlas on September 4, 2025. The European Space Agency's spacecraft also joined the effort. This international coordination shows how valuable interstellar objects are to science. They're like cosmic time capsules, delivering samples from distant systems we could never otherwise visit. Scientists around the world, using instruments on Earth and in space, worked together to gather as much information as possible before this ancient wanderer slipped away forever. On October 3, 2025, 3I Atlas passed remarkably close to Mars, at a distance of only about 28 million kilometers, roughly 17 million miles. This close approach provided a unique opportunity for the flotilla of spacecraft currently studying the Red Planet. NASA's Perseverance and Curiosity rovers, the Mars Reconnaissance Orbiter, the MAVEN spacecraft studying Mars atmosphere, the European Space Agency's ExoMars Trace Gas Orbiter, and the United Arab Emirates Hope Orbiter all had the comet in their field of view. The Perseverance rover, using its Mastcam-Z camera system, captured images showing the ghostly glow of the comet's coma. In these images, the comet appeared as a faint smudge against the Martian sky, its light dimmed by distance but still visible. The ExoMars Trace Gas Orbiter successfully photographed the comet's diffuse coma from orbit. These observations from Mars offered a different perspective than Earth-based telescopes could provide, helping scientists better understand the comet's structure and activity. For a brief time, Mars became an outpost for interstellar comet research, its robotic inhabitants watching a visitor from beyond. As October 2025 progressed, 3I Atlas moved closer to the Sun, and observing it from Earth became increasingly difficult. The comet's position in the sky was moving closer to the Sun's apparent location, creating a bright glare that overwhelmed its faint light. By late September, the comet had entered what astronomers call solar conjunction, meaning it was nearly in line with the Sun from Earth's perspective. For observers on the ground, this meant the comet was lost in the Sun's glare during both day and night. However, this didn't mean observations stopped. Several spacecraft positioned away from Earth continued to track the comet. The Solar and Heliospheric Observatory, known as SOHO, which orbits a stable point in space nearly 1 million miles from Earth, used its coronagraph instruments to block the Sun's bright disk and observe the surrounding space. The Stereo spacecraft, which orbit the Sun at slightly different positions than Earth, also had clear views. Even weather satellites in Earth orbit, like GOES 19, contributed observations using their space weather monitoring instruments. While most of the world waited, these mechanical eyes continued to watch. The geometry of 3I Atlas' passage through our solar system was both scientifically interesting and observationally challenging. Its orbit brought it to perihelion when positioned behind the Sun from Earth's perspective, making observations difficult during that critical time. Such alignments happen occasionally with comets, a natural consequence of orbital mechanics and the timing of discovery. The fact that sky survey telescopes like ATLAS favor searching regions near the ecliptic plane, where most solar system objects orbit, the means were more likely to discover interstellar objects with lower inclinations. Scientists simply waited patiently for the comet to re-emerge from behind the Sun, continuing their studies when viewing conditions improved. This waiting period, though frustrating for eager researchers, is a common part of astronomical work. The universe operates on its own schedule, and patience is required to observe celestial events as they unfold naturally. On October 29, 2025, at approximately 11:47 Universal Time, 3I Atlas reached perihelion. At this moment, the comet was about 1.36 astronomical units from the Sun, equivalent to approximately 126 million miles, or 203 million kilometers. This placed it just inside the orbit of Mars, at a distance where the Sun's radiation becomes intense enough to drive strong outgassing from cometary ices. The solar irradiance at perihelion reached roughly 770 watts per square meter, far greater than the comet had experienced in the cold darkness of interstellar space. For an object that may have spent millions of years in near absolute zero temperatures, moving only through the thin radiation of distant starlight, this was a moment of maximum thermal stress. Ice that had remained frozen since the comet's formation would sublime rapidly into gas. Dust trapped in that ice would be released, forming a bright tail pushed away from the Sun by solar radiation pressure. If the comet's nucleus was weakly bound, held together only by the strength of frozen ice. This intense heating might break it apart into fragments. Scientists eagerly awaited observations to see whether 3I Atlas would survive intact or fragment into pieces during this passage. Observations of 3I Atlas during its approach to perihelion revealed something unexpected. The comet brightened much more rapidly than most comets typically do. A research paper analyzing data from multiple space-based instruments reported that the comet's brightness increased with distance from the Sun, according to an unusually steep relationship. While most comets brighten gradually as they approach the Sun, following predictable patterns based on how much ice they're sublimating. 3I Atlas brightened much faster. The data showed the brightness scaling inversely with distance to the power of -7.5, which is significantly steeper than normal comet behavior. This rapid brightening could have several explanations. Perhaps the comet's surface structure allows for unusually efficient heat absorption. Perhaps layers of ice with different volatilities are being exposed as the comet sheds its outer layers. Or perhaps the composition of ices is different from solar system comets, with more volatile materials mixed in. Whatever the cause, this behavior adds another item to the growing list of unusual properties that make 3I Atlas scientifically intriguing. The reason for this rapid brightening, exceeding that of most Oort cloud comets at similar distances, remains unclear. Scientists continue to analyze the data, searching for explanations. Another surprising observation came from color photometry, performed by Spacecraft, monitoring 3I Atlas near perihelion. As the comet approached its closest point to the Sun, it appeared distinctly bluer than the Sun itself. This was unexpected for several reasons. Dust particles scattered around a comet typically redden reflected sunlight, similar to how Earth's atmosphere makes sunsets appear red. Additionally, the surface temperature of the comet, even when heated by solar radiation, would be perhaps 20 times cooler than the Sun's photosphere, which has a temperature of about 5,800 degrees Kelvin. Cooler objects emit light that's shifted toward the red end of the spectrum, yet 3I Atlas appeared blue. The most likely explanation, according to astronomers analyzing the data, is that gas emission was contributing significantly to the comet's visible brightness. Certain molecules, particularly ionized carbon monoxide and possibly carbon compounds called C2, emit blue light when excited by solar radiation. This blue appearance suggests that gas emission, not just reflected sunlight from dust, was playing a major role in the comet's brightness near perihelion. The chemistry of outgassing was literally changing the color of the light we observed. On the date of perihelion, October 29th, 2025, NASA's Jet Propulsion Laboratory reported the first evidence of non-gravitational acceleration in 3I Atlas's motion. Non-gravitational acceleration is a subtle effect seen in active comets when jets of gas erupting from their surface create small thrust forces, like tiny rocket engines. These forces can nudge the comet slightly off the purely gravitational trajectory predicted by Kepler's laws of orbital motion. The acceleration was detected by Davide Farnocchia, a navigation engineer who specializes in precisely tracking the positions of small bodies in the solar system. The measurements showed two components of acceleration in the orbital plane. There was a radial acceleration away from the Sun of about 135 kilometers per day squared, and a component along the orbital direction. These accelerations are modest, only enough to shift the comet's position by perhaps 10 times Earth's radius over the course of a month, far too small to significantly change its path. For a natural comet, this is exactly what astronomers would expect. As ice sublimates from the sunward side, jets of gas carry momentum, gently pushing the comet. This detection confirms that 3I Atlas is actively outgassing, behaving as comets do. The observation techniques used to study 3I Atlas near perihelion required considerable ingenuity. Because the comet was faint, typically around magnitude 11, which is far too dim to see with the naked eye, scientists had to use image stacking techniques. Multiple photographs taken over time are combined, or stacked, which adds together the faint signal of the comet while averaging out the random noise in each individual image. This is similar to how long-exposure photography can reveal stars too faint to see in a single quick snapshot. Amateur astronomers and professional researchers, including Werkate Boonplod and others, processed images from various spacecraft to track the comet right up to perihelion. The GOES, 19 weather satellite, NASA's Punch constellation, designed to study the Sun's corona, and the venerable SOHO spacecraft all contributed observations. These instruments weren't designed primarily for comet studies. They monitor the Sun and space weather. But their coronagraph instruments, which block the Sun's bright disk to study the surrounding environment, were perfect for observing a faint comet passing near the Sun. Science often advances through creative use of existing tools. The distance of 3I Atlas at discovery, about 410 million miles from the Sun, represents an important milestone in interstellar object detection. The first interstellar visitor, Oumuamua, was discovered in October 2017, as it was already leaving the solar system, racing outward past Earth's orbit. Scientists had only a few weeks to observe it before it became too faint and too distant. They never got to see it approach the Sun or study it during its most active period. The second interstellar object, 2I Borisov, was discovered in August 2019 when it was still approaching, but it was already relatively close by the time it was found. With 3I Atlas, astronomers got lucky. They spotted it while it was still 4.5 astronomical units from the Sun, well before perihelion, giving them months to plan observations. This early detection was possible because sky survey systems like Atlas have become more sensitive, scanning larger portions of the sky more frequently. As new telescopes like the Vera C. Rubin Observatory come online, operating in Chile and equipped with the largest digital camera ever built for astronomy, we can expect to discover many more interstellar visitors. They're not rare. They're just faint and fast-moving, which has made them historically difficult to spot. The trajectory of 3I Atlas through our solar system will bring it close to Jupiter on March 16th, 2026. At that time, the comet will pass within about 54 million kilometers of the giant planet, roughly 34 million miles. This won't be close enough for Jupiter's gravity to significantly alter the comet's path. Remember, 3I Atlas is moving too fast to be captured, even by Jupiter's immense gravitational pull. However, this close approach does offer an observational opportunity. NASA's Juno spacecraft, currently orbiting Jupiter to study its atmosphere and magnetic field, will be in a favorable position to observe the comet. Juno's instruments could potentially image 3I Atlas and even use radio antennas to check for any radio emissions. Though scientists expect to find only the natural radio waves that active comets sometimes produce when solar wind particles interact with gases in their coma. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, traveling toward the Jupiter system, will also have observation opportunities. In early November 2025, JUICE was positioned along a favorable line of sight at about 0.4 astronomical units from the comet, allowing its instruments to study the interstellar visitor as it began its outbound journey from perihelion. The closest approach of 3I Atlas to Earth will occur on December 19, 2025, just 6 days before Christmas. On that date, the comet will pass at a distance of approximately 267 million kilometers, about 166 million miles, or roughly 1.8 astronomical units from our planet. To put this in perspective, that's about 1.8 times the distance from Earth to the Sun. The comet poses absolutely no danger. It will remain far beyond the orbit of the Moon, far beyond the paths of all Earth-orbiting satellites. But from a scientific perspective, this will be an important moment. By mid-December, 3I Atlas will have emerged from behind the Sun as seen from Earth, reappearing in the dawn sky. Ground-based telescopes will have their best opportunity to observe it since September. The Hubble Space Telescope and the James Webb Space Telescope will turn their instruments toward the comet, gathering high-resolution images and spectra. Hundreds of smaller telescopes at professional observatories and amateur astronomy sites around the world will also observe, contributing data to a global effort to understand this visitor. The observations during December will allow scientists to see how perihelion passage changed the comet, whether it survived intact, and whether its activity increased or decreased after leaving the Sun's intense radiation behind. The term interstellar space refers to the vast regions between star systems where the density of matter falls to just a few atoms per cubic centimeter. Our Sun's influence extends outward in what's called the heliosphere, a bubble carved out by the solar wind, a stream of charged particles flowing from the Sun. The boundary of the heliosphere, called the heliopause, lies roughly 120 astronomical units from the Sun, in the direction of the Sun's motion through space, about 3 times the distance to Pluto. Beyond this boundary begins true interstellar space, where the Sun's particles mix with the interstellar medium, the thin gas and dust that fills the space between stars. 3I Atlas came from out there, from the dark between the stars. It traveled for perhaps millions of years in temperatures hovering just above absolute zero, experiencing only the faint radiation of distant starlight and the cosmic microwave background. No planets were nearby to tug on it with gravity. No star heated its surface. It simply drifted, one tiny icy body among billions, until by chance, its trajectory intersected with our solar system. The journey from its home star system to ours could have taken tens of millions of years, maybe longer, depending on where it originated and what speed it traveled before the Sun's gravity accelerated it further. Understanding the origin point of 3I Atlas requires working backward from its current trajectory. Astronomers break down the comet's motion into 3 velocity components, using a coordinate system aligned with our galaxy. These components are called U, V, and W, representing motion toward or away from the galactic center, motion in the direction of galactic rotation, and motion perpendicular to the galactic plane. When 3I Atlas arrived at the solar system, it was moving away from the galactic center with a velocity of about -51 kilometers per second relative to the Sun, moving upward through the galactic plane. By tracing this motion backward, astronomers can estimate the general region of the galaxy where the comet might have originated. However, the uncertainties grow quickly. Stars and clouds of gas exert tiny gravitational tugs. Over millions of years, these small influences compound, making it nearly impossible to identify a specific star system as the comet's birthplace. The best we can say is that it came from somewhere in the galactic neighborhood, within perhaps a few hundred light years. It's an anonymous wanderer, its home star lost to time and distance. The Atlas survey system that discovered this interstellar comet consists of multiple robotic telescopes working together to scan the sky every night. The name Atlas stands for Asteroid Terrestrial Impact Last Alert System, and it was originally designed to detect asteroids that might pose an impact threat to Earth. These telescopes are relatively small by astronomical standards, but their strength lies in the width of their field of view and how frequently they observe each patch of sky. By comparing images taken on different nights, the Atlas software can detect anything that moves. On July 1st, 2025, the Atlas telescope at Rio Hurtado, Chile, flagged an object with the temporary designation A11P-L3Z. Its motion seemed unusual, too fast, and at an odd angle compared to typical asteroids. Astronomers around the world were alerted. Within hours, other telescopes confirmed the detection. Additional checking revealed pre-discovery images of the same object from late June. By carefully measuring the object's position over multiple nights, astronomers calculated its orbit. The calculations showed clearly that this was not just another asteroid. This was something special. A visitor from beyond. By the time 3I Atlas was officially designated on July 2nd, 2025, the Minor Planets Center, the international organization responsible for collecting and cataloging observations of asteroids and comets, had received 122 separate observations from 31 different observatories. This rapid response shows how the astronomical community works together when something important is detected. Observatories on multiple continents, using telescopes of different sizes and types, all contributed data. Some observers used large research telescopes at professional observatories. Others were experienced amateur astronomers with well-equipped backyard setups. The data from all these sources was compiled, analyzed, and confirmed. The object received 2 designations: 3I Atlas, marking it as the 3rd confirmed interstellar object, and C/2025 N1 Atlas, which is the standard naming convention for comets discovered in 2025 during the second half of June, designated by the letter N. These naming conventions might seem dry and bureaucratic, but they represent a centuries-old tradition of careful record-keeping, ensuring that discoveries are properly documented and credited. Every comet, every asteroid, every small body in our solar system receives its designation and becomes part of the permanent record of human knowledge. And now, let's pause for just a moment. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the telescopes we point at the sky, the comets we discover, all made from the material of the universe. Returning to the universe, feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronomers breathed while watching 3I Atlas drift across their telescope images. We are all space travelers, flying on a small planet through the galaxy, watching other travelers pass by. Now we continue. The spectrum of light from a comet contains information about its chemical composition. When atoms and molecules in the coma are energized by solar radiation, they emit light at very specific wavelengths, creating what astronomers call spectral lines. Different elements and compounds produce different patterns of lines, like fingerprints. By spreading the light from 3I Atlas through a spectrograph, scientists could identify the presence of water vapor, carbon compounds, and metals like nickel. These observations required large telescopes with sophisticated instruments, like the Very Large Telescope in Chile, which consists of 4 main telescopes, each with mirrors 8.2 meters in diameter. The spectrographs attached to these telescopes can detect incredibly faint signals, measuring the brightness at thousands of different wavelengths simultaneously. The data appears as graphs showing peaks and valleys, each peak corresponding to a specific molecule or atom, releasing its characteristic light. Through this technique, astronomers can analyze the chemistry of a comet without ever touching it, reading its composition from across hundreds of millions of miles of empty space. The coma of a comet can extend for hundreds of thousands of miles into space, even though the nucleus might be only a few miles across. This enormous cloud of gas and dust is what makes comets visible from Earth, even when they're far from the sun. The gas molecules in the coma absorb sunlight and re-emit it at specific wavelengths, particularly in the ultraviolet range. For 3I Atlas, the hydroxyl emission detected by the Swift Observatory came from water molecules that had been broken apart by solar radiation. The strong ultraviolet signal suggested that something unusual was happening. Perhaps sunlight was heating small icy grains released from the nucleus, allowing them to vaporize gradually as they drifted outward. This would create an extended source of water vapor, different from the typical concentrated fountain near a comet's nucleus. Such extended sources have been seen in only a handful of distant comets, and they point to complex, layered ice structures that preserve clues about how these objects formed billions of years ago in the cold outer regions of a planetary system. The tail of a comet has 2 components, though they're not always both visible. The dust tail forms as tiny particles, no longer held by the comet's weak gravity, are pushed outward by the pressure of sunlight. Yes, light has pressure. Photons carry momentum, and when they bounce off or are absorbed by dust grains, they transfer that momentum, pushing the particles away from the sun. The dust tail curves slightly, following the comet's orbit, creating the classic sweeping arc we see in photographs. The gas tail, or ion tail, is different. It's composed of ionized molecules, atoms that have lost electrons due to solar radiation. These ions are affected by the solar wind, the stream of charged particles flowing from the Sun, and they stream almost straight away from the Sun, regardless of the comet's direction of motion. Ion tails can stretch for millions of miles, glowing with a bluish hue from fluorescent gases. For 3I Atlas, both types of tails were observed, their structure and brightness changing as the comet moved closer to and then away from the Sun. The nucleus of a comet, the solid core beneath the coma and tails, is darker than most people imagine. Cometary surfaces are typically as dark as asphalt or coal, reflecting only 3 to 5% of the light that hits them. This darkness comes from complex organic molecules, carbon-based compounds created by radiation processing of ices over billions of years. When fresh ice is exposed to space radiation and solar wind, chemical reactions slowly build up a dark crust of these organic materials. This crust insulates the interior, slowing the rate at which deeper ice can sublime. However, as the crust thickens, it can crack and break, exposing fresh, bright ice beneath. The contrast creates a patchwork surface of dark and light regions. For 3I Atlas, astronomers haven't yet been able to see the nucleus clearly enough to map its surface, hidden as it is within the bright coma. But from studying similar comets, they can infer that its surface is likely ancient, darkened by billions of years in space, occasionally fracturing to reveal the pristine ice within. Temperature plays a crucial role in cometary activity. Different ices sublime at different temperatures. Water, ice, the most abundant volatile in most comets, remains frozen until the surface temperature reaches around 200 Kelvin, approximately -73 degrees Celsius. But other compounds are more volatile. Carbon dioxide ice sublimates at lower temperatures, around 150 Kelvin. Carbon monoxide is even more volatile, beginning to sublime at just 25 Kelvin, barely above absolute zero. When 3I Atlas was far from the Sun, in the cold depths of interstellar space, its temperature would have been close to 3 Kelvin, the temperature of the cosmic microwave background radiation that fills the universe. As it entered our solar system and moved toward the Sun, different layers of ice began activating at different distances. First carbon monoxide, then carbon dioxide, and finally water as the comet warmed. This sequence creates changes in activity and color as different gases dominate the coma at different times. Scientists studying the evolution of 3I Atlas's coma could see these changes, tracking how the chemistry shifted as the Sun's warmth penetrated deeper into the ancient ice. The rotation of a comet affects how and where gas jets form on its surface. As the nucleus spins, different regions face the Sun at different times, creating a pattern of heating and cooling. If the rotation is slow, one side can become very hot, while the other remains cold. If the rotation is fast, the temperature differences are less extreme. For 3I Atlas, observations suggested a rotation period of about 16.2 hours, meaning the comet completes one full spin roughly every 16 hours. This moderate rotation rate allowed sunlight to heat each part of the surface in turn, driving outgassing from different locations as the comet rotated. The jets of gas and dust erupting from active regions create torque, slightly changing the rotation rate over time. This spin-up or spin-down can be measured precisely, and it provides information about the size and activity of the jets. For scientists, the rotation period is another piece of the puzzle, helping them understand the shape, structure, and activity patterns of this distant visitor. The weak gravity of a comet's nucleus means that even small forces can have significant effects. The nucleus of 3I Atlas, even if it's several miles across, has gravity only a tiny fraction of Earth's. A person standing on its surface, if that were possible, would weigh perhaps a few ounces at most. They could easily jump into space with a gentle push. This weak gravity also means that dust and gas released from the surface quickly escape into space rather than falling back down. Larger particles might linger briefly, bouncing along the surface in slow arcs before drifting away. The nucleus can't hold onto an atmosphere. Everything released eventually leaves. This is why comets gradually lose mass each time they pass near the Sun. With every perihelion passage, more ice sublimates, more dust escapes, and the comet slowly evaporates away. Over millions of years, a comet can lose significant portions of its original mass, eventually becoming a dormant rocky core surrounded by a debris field, or breaking apart entirely. The discovery of interstellar objects like 3I Atlas has changed our understanding of what moves through the space around us. Astronomers now estimate that at any given time, several interstellar objects are passing through the inner solar system, within the orbit of Jupiter. Most of them are too small and faint to detect with current technology. They pass through unseen, anonymous wanderers in the dark. But, as our telescopes improve, we're beginning to catch them. The Vera C. Rubin Observatory, which began operations in 2025, is a revolutionary new telescope in Chile, equipped with a 3.2 gigapixel camera, the largest digital camera ever built for astronomy. It can image the entire visible sky every few nights, creating a movie of the universe. With this capability, astronomers expect to discover dozens, perhaps hundreds, of interstellar objects over the coming decade. Each one will be a treasure, a sample from a distant star system delivered to our doorstep at no cost. The universe, it turns out, is constantly sharing its contents, sending messengers between the stars. The long journey of 3I Atlas through interstellar space exposed it to cosmic rays, high-energy particles that permeate the galaxy. These particles, mostly protons and atomic nuclei, moving at nearly the speed of light, constantly bombard any object in space. Over millions of years, this radiation causes chemical changes in the surface layers of ice and dust. Simple molecules like water, methane, and ammonia can be transformed into more complex organic compounds. The darkening of cometary surfaces is partly due to this radiation processing. Additionally, tiny impacts from dust grains moving through interstellar space gradually erode the surface, microscopically cratering and roughening it. By the time 3I Atlas arrived at our solar system, its outer layers had been aged by its journey, carrying the scars of millions of years in the void. Scientists analyzing the composition of its coma hope to find signatures of this processing, comparing interstellar comets to solar system comets to understand how their environments differ. The concept of an Oort cloud helps explain where long-period comets in our own solar system come from. The Oort cloud is a vast spherical shell of icy bodies surrounding the Sun at enormous distances, perhaps 50,000 to 100,000 astronomical units away. These objects, billions of them, are the debris left over from our solar system's formation. They orbit so far from the Sun that their motion is barely bound by its gravity. Occasionally, gravitational perturbations from passing stars or the tidal force of the galaxy itself nudge an Oort cloud object inward. It falls toward the Sun, becoming a long-period comet visible from Earth. Other star systems likely have similar clouds of icy debris in their outer reaches. When planets form and migrate, their gravity can fling some of these objects outward with enough speed to escape entirely, becoming interstellar travelers. 3I Atlas may be such an object, expelled from another star's Oort cloud analog long ago, now passing through ours by chance. The velocity of 3I Atlas relative to the local standard of rest, the average motion of stars in our part of the galaxy, provides clues about its origin. The local standard of rest represents the mean velocity of stars in our solar neighborhood as they orbit the galactic center. Objects that formed within this neighborhood, like comets from the Oort cloud, have velocities close to this standard. But 3I Atlas's velocity is noticeably different. It's moving faster in certain directions, suggesting it may have come from a region of the galaxy with different average stellar motions. Perhaps it formed around a star in a younger stellar cluster, where stars move faster relative to older field stars. Or perhaps it was accelerated by a close encounter with a massive object during its journey. The velocity vectors paint a picture of wandering, of a long path through the galaxy, with multiple gravitational encounters, bending and changing its trajectory, until, finally, it encountered our Sun. The albedo of an object describes how much light it reflects. A perfect mirror has an albedo of 1, reflecting all light. A perfect absorber, like a black hole, has an albedo of 0. Most asteroids have albedos between 0.03 and 0.3, depending on their composition. Cometary nuclei, as mentioned, tend to be very dark, with albedos around 0.03 to 0.05. This low albedo makes them difficult to detect when they're far from the Sun and not outgassing. The brightness we observe depends on both the size of the nucleus and its albedo. A large, dark object can be as bright as a small, light-colored object. For 3I Atlas, astronomers estimated the size by combining measurements of total brightness with assumptions about albedo based on other comets. If the albedo is at the low end, around 0.03, the nucleus could be as large as 3.5 miles across. If it's at the high end, perhaps 0.06, the nucleus might be closer to half a mile. This uncertainty will likely persist until higher resolution observations, perhaps with radar or very close spacecraft flybys, can directly measure the size. The energy budget of a comet near the Sun is dominated by incoming solar radiation. At Earth's distance from the Sun, the solar flux is about 1,361 watts per square meter, enough to power several light bulbs per square meter of surface. At 3I Atlas, perihelion distance of 1.36 AU, the flux is somewhat less, around 770 watts per square meter. This energy heats the surface, but much of it goes into sublimating ice rather than raising the temperature. Sublimation is an endothermic process, meaning it absorbs heat. As ice sublimates, it cools the surface, creating a balance between incoming solar energy and the cooling effect of evaporation. This is why cometary surfaces don't become as hot as you might expect. Even at perihelion, the sunlit side might only reach temperatures of 200 to 300 Kelvin, far cooler than, say, the Moon's daytime temperature. This energy balance determines how active a comet becomes, how much gas and dust it releases, and how bright it appears from Earth. The question of whether 3I Atlas will survive perihelion intact depends on the strength of its nucleus. Some comets are loose aggregations of smaller fragments, held together weakly by their own feeble gravity and the strength of ice acting as cement. When heated strongly at perihelion, the ice binding them together can sublime away, causing the nucleus to split into multiple pieces. Other comets have survived perihelion passages, their nuclei strong enough to withstand the forces. For 3I Atlas, scientists awaited post-perihelion observations to see whether the nucleus remained whole or had broken into fragments. A breakup would be scientifically interesting, exposing fresh interior material. Survival would indicate a strong, coherent nucleus. The answer would come in December, when the comet re-emerged into view. The study of interstellar objects is still in its infancy. With only 3 confirmed interstellar visitors so far, astronomers are just beginning to understand the diversity of these objects. Each one discovered has been different. Oumuamua was small, reddish, and elongated, showing no signs of cometary activity despite its odd acceleration. 2I Borisov was clearly a comet, with a coma and tail, and its composition closely resembled solar system comets. Now, 3I Atlas appears to be another comet, but with unusual properties. Early water release, nickel vapor, rapid brightening, and a blue appearance near perihelion. Are these differences due to different formation environments in different star systems, or are they simply the natural variation among comets, whether interstellar or solar? With such a small sample size, it's hard to say. But each new discovery adds to the dataset, slowly revealing the population of objects wandering between the stars. In a few decades, when dozens or hundreds have been catalogued, patterns will emerge. Well, begin to understand what's typical and what's rare among these travelers from afar. If you're still here, still awake, still drifting with us through these stories, take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together. You and I and everyone listening in the quiet dark. Floating through facts like asteroids drifting through the void. There's no rush, no destination. Just the gentle momentum of curiosity carrying us forward. Let's continue. Amateur astronomers played an important role in observing 3I Atlas, while large professional telescopes gathered detailed spectra and high-resolution images. Hundreds of smaller telescopes, operated by dedicated amateurs, also tracked the comet. These observers used telescopes ranging from 8-inch reflectors to larger 16-inch instruments, equipped with sensitive CCD cameras. By stacking multiple images and carefully processing the data, they could detect the faint glow of the comet and measure its position accurately. Their observations, submitted to international databases like the Minor Planet Center, contributed to refining the comet's orbital calculations. This citizen science aspect of astronomy is valuable. Professional observatories have limited time available, and they can't monitor every object continuously. Amateur astronomers fill the gaps, providing crucial data. In the case of 3I Atlas, their dedication ensured continuous tracking through different phases of its passage, documenting its changing brightness and appearance. The concept of a gravity assist, sometimes called a gravitational slingshot, is how spacecraft gain speed by flying close to planets. As a spacecraft approaches a planet, it falls into the planet's gravitational field, gaining speed. If the trajectory is carefully planned, the spacecraft can swing around the planet and fly away in a different direction, carrying extra velocity stolen from the planet's orbital motion. This technique has been used for decades to send spacecraft to distant destinations. For 3I Atlas, perihelion represented a moment of maximum gravitational influence from the Sun. The Sun's gravity bent the comet's path, changing its direction slightly, while the comet's tremendous speed carried it onward. This natural gravitational interaction is simply physics at work, the same principles that govern all motion in the solar system. The color of an object in space tells us about its surface composition. Reddish colors often indicate the presence of complex organic molecules, similar to those found on many asteroids and outer solar system moons. Grayish or neutral colors suggest rocky or metallic surfaces. Bluish colors are rare and usually indicate fresh ice or specific gas emissions. Early observations of 3I Atlas showed it was slightly reddish, typical for a comet with an aged surface crust. But near perihelion, as mentioned earlier, it became distinctly blue. This color change tracked the evolution of its activity, showing that gas emission from species like ionized carbon monoxide was dominating the light we observed. Color measurements require careful calibration. Astronomers use filters that isolate specific wavelengths of light, then compare brightnesses through different filters to calculate color indices. These numbers can then be translated into physical properties, revealing the processes at work on a distant object. The term exoplanet refers to planets orbiting stars other than our Sun. Since the first confirmed detection, in 1995, thousands of exoplanets have been discovered. Some are gas giants larger than Jupiter. Others are rocky worlds similar to Earth. A few orbit in their star's habitable zone, the region where temperatures allow liquid water to exist. The existence of exoplanets tells us that planetary systems are common in the galaxy. And if planets form, then debris from planet formation, objects like comets and asteroids, must also be common. When those planetary systems evolve, gravitational interactions can eject some of this debris, sending it wandering through interstellar space. 3I Atlas is almost certainly debris from an exoplanetary system. Somewhere out there, perhaps a few hundred light years away, perhaps farther, is a star with planets. Those planets grew from a disk of gas and dust. 3I Atlas formed in that same disk, then was cast out, becoming a wanderer. It's a refugee from another world. Spectroscopy is one of the most powerful tools in astronomy. By spreading light into its component colors and measuring the intensity at each wavelength, astronomers can determine temperature, composition, velocity, and even magnetic field strength of distant objects. The technique has been refined over more than a century. Modern spectrographs use sophisticated detectors that can measure thousands of wavelengths simultaneously with high precision. For 3I Atlas, spectra, obtained by instruments like those on the Very Large Telescope, revealed the presence of specific molecules and atoms. Each spectral line corresponds to a quantum transition, an electron jumping between energy levels in an atom or a molecule, vibrating or rotating in a specific way. By identifying these lines and measuring their strengths, scientists can determine not just what's present, but how much of each substance is there. It's like chemical analysis from across the solar system, reading the composition of a comet without ever touching it. The solar wind is a stream of charged particles, mainly protons and electrons, flowing outward from the Sun at speeds around 400 kilometers per second. This wind is thin, with a density much lower than Earth's atmosphere, but it extends throughout the solar system and beyond, creating the heliosphere. When the solar wind encounters a comet's coma, it interacts with the gases there, pushing on the ions and creating the ion tail. The solar wind can also compress the coma on the sunward side and stretch it out behind the comet, creating the characteristic teardrop shape seen in images. For 3I Atlas, the interaction with the solar wind was particularly strong near perihelion, when the comet's outgassing was most intense and the solar wind density was highest. These interactions can be studied using spacecraft, like the Parker Solar Probe and Solar Orbiter, which measure the solar wind properties directly, providing context for understanding how it affects comets. The brightness of a comet is measured in magnitude, the same system used for stars. Lower numbers indicate brighter objects. The brightest star in the night sky, Sirius, has a magnitude of about -1.5. The faintest stars visible to the unaided eye under dark skies are around magnitude 6. 3I Atlas, at its brightest near perihelion, reached around magnitude 11, which is far too faint to see without a telescope. You'd need at least a 6-inch telescope and moderately dark skies to spot it. This faintness is typical for interstellar visitors. They're small, distant, and not particularly reflective. Only if an interstellar comet happened to pass very close to Earth and Sun simultaneously would it become bright enough for naked eye viewing. Such an event would be spectacular, a once-in-history occurrence. But most interstellar objects, like 3I Atlas, remain the domain of telescopes and dedicated observers. The ephemeris of a celestial object is a table predicting its position in the sky at future times. Astronomers compute ephemerides based on orbital calculations, allowing observers to know exactly where to point their telescopes. For newly discovered objects like 3I Atlas, the ephemeris is initially uncertain because only a few observations have been made. As more data accumulates, the orbit becomes better defined, and the ephemeris becomes more accurate. Within weeks of 3I Atlas's discovery, its ephemeris was precise enough to predict its position months in advance. This allowed observers to plan observations, and it allowed spacecraft missions to determine whether they'd have favorable viewing geometry. The ephemeris calculations involve complex mathematics, accounting for the gravitational pulls of the Sun, planets, and sometimes even asteroids if the object passes close to them. Modern computers handle these calculations routinely, but the underlying principles go back centuries to the work of Kepler and Newton. Light takes time to travel. When we observe 3I Atlas, we see it as it was when the light left it, not as it is right now. At a distance of dime, say 300 million miles, light takes about 26 minutes to reach us. This means when scientists observed the comet on a given night, they were seeing it as it was 26 minutes earlier. For most purposes, this delay is negligible. But for rapidly changing phenomena, like outbursts where a comet suddenly brightens, this light travel time matters. It introduces a delay between when something happens and when we observe it. Conversely, any signals we might send outward, say radio transmissions, would take the same time to reach that distance. Space is vast, and even at the speed of light, communication across solar system distances requires patience. This fundamental limitation shapes how we explore and study distant objects. The study of comets has a long history in human civilization. Ancient peoples saw comets as omens, interpreting their appearances as signs of coming events, good or bad. The word comet comes from the Greek word meaning hair, describing the flowing tail that resembles hair streaming in the wind. For most of history, people didn't understand what comets were. Aristotle thought they were atmospheric phenomena, disturbances in Earth's air. It wasn't until the 16th century that astronomers like Tycho Brahe demonstrated that comets were far beyond Earth's atmosphere, traveling through interplanetary space. Isaac Newton showed that comets follow the same laws of motion and gravity as planets, orbiting the Sun in elongated paths. Edmund Halley used Newton's laws to predict that a particular comet would return in 1758, and when it did, it proved that comets are periodic visitors, not random signs. Now we know even more. Some comets come from our own Oort cloud, while others, like 3I Atlas, are visitors from other stars. Our understanding has expanded from fear and wonder to detailed scientific knowledge. Yet the wonder remains. We've traveled halfway. And in this moment, let each breath guide you to realize, time is yours, a separate stream that only you are living, while the vast universe continues to spin, expand, change. This second you're breathing, listening, is unique. 3I Atlas traveled for millions of years to reach this moment. And you are here to witness it. Cherish the present moment, knowing that right now, your time is unique in the universe, and we continue drifting. The night sky appears fixed, unchanging from night to night. The constellations our ancestors saw are the same we see now. But this constancy is an illusion of scale. Everything is moving. Stars orbit the galactic center. Our sun drifts through the local stellar neighborhood at 12 miles per second. The galaxy itself rotates, taking 230 million years to complete one orbit. On human timescales, these motions are imperceptible. But over millions of years, the sky transforms completely. Stars that formed together drift apart. New stars are born from collapsing clouds. Old stars die in supernova explosions or quiet fades. Through all this motion, objects like 3i Atlas wander, crossing paths with different stars, seeing different skies, journeying through an ever-changing galaxy. It's a cosmic dance, slow and grand. Every comet is unique, shaped by its individual history. Some formed close to their star and were kicked outward. Others formed far away in the cold outer regions. Some experienced collisions that reshaped them. Others remained pristine for billions of years. The diversity we see in comets, even those from our own solar system, reflects this variety of histories. 3i Atlas carries its own unique story in its composition and structure. The nickel detection, the early water activity, the rapid brightening, each is a clue. Scientists piece these clues together like detectives, trying to reconstruct the comet's biography. Where did it form? What conditions existed there? How long did it wander? What did it experience during that journey? The answers are still emerging. Dust particles released from comets can persist in space for millions of years. They slowly spiral inward toward the sun due to radiation pressure and the Poynting-Robertson effect, a subtle drag caused by asymmetric absorption and re-emission of sunlight. These dust grains eventually create meteor streams that Earth passes through annually, producing familiar meteor showers like the Perseids and Leonids. The dust from 3i Atlas will also persist, spreading along its orbital path. However, because it's on a hyperbolic trajectory leaving the solar system, this dust won't create a meteor shower on Earth. It will disperse into interstellar space, perhaps eventually encountering another star system billions of years from now, carrying a faint trace of its passage through our neighborhood. The idea that life might be distributed through space by comets and asteroids is called panspermia. The hypothesis suggests that simple organisms or organic molecules could survive inside comets, protected from radiation by layers of ice and rock, and be delivered to planets when comets impact. There's no direct evidence for this, but experiments show that some hardy microorganisms can survive the vacuum and radiation of space. Organic molecules, including amino acids, have been found in meteorites. Comets are known to contain complex organic compounds. Whether 3i Atlas carries any organic molecules, we don't yet know. But it's possible. If so, these molecules formed in another star system, under different conditions, perhaps with chemistry unlike anything on Earth. The comet becomes a cosmic laboratory, showing us what's possible elsewhere. The word wander comes from the same root as wonder. To wander is to move without fixed destination, to explore freely. 3i Atlas is a wanderer in the truest sense, drifting through the galaxy, not bound to any star. This freedom comes at a cost. It will never orbit a star long enough to experience stable conditions. It will never participate in the gradual processes that shape planetary systems over billions of years. It's a perpetual outsider, passing through but never staying. Yet in its wandering, it connects different parts of the galaxy, carrying material from one region to another. It's a traveler, a messenger, a link between stellar systems that would otherwise remain forever separate. The phases of cometary activity follow a pattern. Far from the Sun, a comet is dormant, cold and inactive. As it approaches, the most volatile ices begin to sublime, creating a faint coma. Closer still, water ice activates, and the comet brightens dramatically. At perihelion, activity reaches maximum. Then, moving away from the Sun, the process reverses. Water activity declines first, then carbon dioxide, and finally, the comet returns to dormancy. For 3I Atlas, this cycle will never repeat. It passes the Sun once and continues outward. In a few years, it will fade beyond detection, growing cold again as it returns to interstellar space. The brief period of activity, from June to December 2025, is the only time we'll ever see it alive. The size of the observable universe is about 93 billion light-years in diameter. Within that vast volume exist an estimated 2 trillion galaxies, each containing billions or trillions of stars. Around those stars orbit planets and smaller bodies. The number of comets in the universe is uncountable. Yet each one, including 3I Atlas, is unique. Each has its own trajectory, its own history, its own composition. The universe creates infinite variation. No two snowflakes are identical, and no two comets are either. This uniqueness gives each discovery meaning. When we study 3I Atlas, we're not just learning about one object. We're sampling the diversity of the universe, one small piece at a time. Silence in space is absolute. Sound requires a medium, air or water, or some material to carry vibrations. But space is a near-perfect vacuum. There's no air to carry sound waves. If you could float beside 3I Atlas as it orbited the Sun, you would hear nothing. Not the roar of outgassing jets, not the crack of ice fracturing from thermal stress, not the impact of dust grains hitting the surface. Only silence. Yet this silence is peaceful, not empty. Light fills space, carrying energy and information. Gravity reaches across vast distances, guiding motion. Magnetic fields thread through the vacuum. Space is quiet but full of invisible forces. A serene dance of physics playing out in complete soundlessness. The future trajectory of 3I Atlas is predictable for decades, perhaps centuries. Astronomers can calculate its path, accounting for the gravity of the Sun and planets. Eventually, it will pass beyond Neptune's orbit, then beyond the Kuiper belt, then beyond the heliopause, into true interstellar space. But on longer timescales, millions of years, the trajectory becomes uncertain. Small gravitational tugs from distant stars, passage through molecular clouds, the tidal force of the galactic disk, all these will deflect it slightly, compounding over time into large changes. We can't say where 3I Atlas will be a billion years from now. It might encounter another star system, passing through much as it passed through ours. Or it might wander forever in the dark between stars, never again feeling the warmth of sunlight. The concept of home for 3I Atlas is complicated. It formed around another star billions of years ago, but that star has since moved. the galaxy rotates differentially, meaning inner regions orbit faster than outer regions. Over billions of years, stars born together drift apart. The star where 3I Atlas formed is now somewhere else in the galaxy, perhaps hundreds of light years away from the comet's current path. In a sense, the comet is homeless, disconnected from its origin. Yet it carries its birthplace within its composition. The isotopes of its atoms, the molecules in its ice, the minerals in its dust, all reflect the environment where it formed. In that sense, it can never truly leave home. It is made of home. Light from distant galaxies takes billions of years to reach us. We see those galaxies as they were in the ancient past, when the universe was young. In comparison, light from 3I Atlas takes mere minutes. But the comet itself is old, possibly older than our solar system. It formed perhaps 4.6 billion years ago, or even earlier, in a stellar system that predates our Sun. So, when we observe it, we're seeing something ancient illuminated by light from now. Past and present merge in our observations. The comet's material is billions of years old, but the light we see is fresh. Time layers in complex ways when we study the cosmos. The heliosphere, the bubble of solar wind surrounding the Sun, has a boundary called the heliopause, located about 120 astronomical units away in the direction of the Sun's motion through space. NASA's Voyager 1 spacecraft crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. These spacecraft are traveling outward at about 3.5 astronomical units per year. 3I Atlas, moving much faster, will cross the heliopause in just a few years. By 2030 or so, it will leave the heliosphere and return to the interstellar medium. There will be no dramatic change, no visible boundary, just a gradual fading of the solar wind and a slight increase in the density of interstellar particles. The comet won't notice. But by crossing that boundary, it will once again become a truly interstellar object, no longer influenced by our Sun. The gravity of our galaxy shapes the motion of everything within it. The Milky Way contains an estimated 100 to 400 billion stars, plus enormous amounts of dark matter and gas. All this mass creates a gravitational field that governs the motion of stars and smaller objects. 3I Atlas, though not bound to our Sun, is still moving within the galaxy's gravitational potential. Its path is influenced by the overall mass distribution of the Milky Way. In a sense, it's in a very wide orbit around the galactic center, taking hundreds of millions of years per orbit. As it wanders between stars, it's still part of the larger structure, a small component of the galaxy's immense dance. Temperature in space is a subtle concept. In direct sunlight, an object can be warm, heated by solar radiation. In shadow, without a nearby heat source, an object cools toward the temperature of the cosmic microwave background, about 2.7 Kelvin, just above absolute zero. There's no air to conduct heat away, so cooling is slow, happening only through thermal radiation. 3I Atlas, far from the Sun in interstellar space, would have been near this background temperature. Then, Entering the solar system, sunlight warmed its surface, creating the temperature contrast that drives outgassing. After perihelion, as it recedes, it will cool again, gradually returning to the cosmic cold. This cycle of warming and cooling is a rare experience for an interstellar object, a brief summer in a life of perpetual winter. Humans have always looked up and wondered. Ancient peoples told stories about the stars, creating myths to explain the patterns they saw. They tracked the motions of planets, predicted eclipses, and marked the passage of seasons by the sky. This tradition of observation continues today, though our tools have changed. Instead of naked eyes and simple sighting instruments, we use telescopes that see across the electromagnetic spectrum, spacecraft that travel to distant worlds, and computers that analyze vast amounts of data. But the fundamental impulse remains the same. We look up, we wonder, we try to understand. 3I Atlas is part of that ancient story, a new chapter in humanity's long conversation with the cosmos. Every photon of light that we detect from 3I ATLAAS began its journey when it was emitted or reflected from the comet. That photon traveled through space at the speed of light, a constant 299,792 kilometers per second, crossing millions of miles without ever slowing down. When it finally reached a telescope on Earth or in space, it struck a detector, transferring its tiny amount of energy and creating a signal. From that single photon, combined with billions of others, we reconstructed an image or a spectrum. All of our knowledge of distant objects comes from photons, light messengers carrying information across the void. It's remarkable that something so insubstantial, a quantum of energy with no mass, can tell us so much. The concept of entropy, the measure of disorder, says that isolated systems tend toward increasing disorder over time. Comets exemplify this. A newly formed comet is ordered, with distinct layers of ice and dust, perhaps a solid interior. Over billions of years, radiation, processing, impact, and internal heat redistribute materials, increasing disorder. The surface becomes rougher, craters accumulate, layers mix. Then, when the comet approaches a star, outgassing removes material, further disrupting its structure. Entropy increases. Eventually, if a comet makes enough passes near a star, it evaporates completely. Its material spread as gas and dust throughout the solar system. Order dissolves into disorder. Yet, in a way, this disorder creates new order. The dust from comets becomes part of new star systems, new planets, perhaps even new life. The cycle continues. Patience is necessary in astronomy. Events unfold on timescales far beyond human lifespans. Stars take millions of years to form and billions of years to die. Galaxies collide over hundreds of millions of years. Even within our solar system, orbital periods of distant objects can be thousands of years. For 3I Atlas, patience was required to track its journey. Months of observation, night after night, watching it move slowly across the sky. Analyzing data, waiting for results from distant spacecraft, building up statistics. The reward for patience is understanding. By waiting and watching, scientists learned about this interstellar visitor, adding a small piece to the vast puzzle of the universe. The elements that make up everything around us go through cosmic cycles. They form in stellar cores, scatter through space when stars die, then gather again in new clouds that birth new stars and planets. Earth itself contains materials from thousands of different stars that exploded billions of years ago. Each atom has a history, a journey through space and time. When you look at 3I Atlas, you're seeing matter that cycled through a different stellar forge, following a different path, yet made of the same fundamental building blocks that exist throughout the universe. Matter connects everything, binding separate stories into one cosmic narrative. We're all part of this grand recycling program, this endless transformation of substance from one form to another. The rarity of interstellar object detections is changing. Before 2017, 0 interstellar objects had been confirmed. Then Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas in 2025. The rate is accelerating, but not because interstellar objects are becoming more common. They're just as common as they've always been. We're getting better at finding them. Improved telescopes, better software, dedicated survey programs, all these increase our detection rate. In the near future, we might discover several interstellar objects per year. They'll become routine, no longer headline news. But each one will still be scientifically valuable, a sample from another stellar system. Routine doesn't mean unimportant. Gravitational lensing occurs when light from a distant object passes near a massive object like a star or galaxy. The mass bends space, curving the light's path. This can magnify, distort, or create multiple images of the background object. Gravitational lensing has been used to study distant galaxies, detect exoplanets, and test Einstein's general relativity. For a small object like 3I Atlas, its mass is far too small to produce any lensing effect. But, in a poetic sense, the comet is like a lens anyway. It focuses our attention, bending the trajectory of human curiosity toward understanding interstellar space. It makes us look more carefully, think more deeply, and wonder about the larger universe beyond our small solar system. The aurora borealis and aurora australis, the northern and southern lights, occur when charged particles from the sun collide with Earth's atmosphere, exciting atoms and causing them to glow. These displays are beautiful, colorful curtains of light dancing across the polar skies. Comets produce a different kind of glow. Sunlight ionizes molecules in their coma, causing fluorescence. Atoms absorbing photons and re-emitting them at specific wavelengths. The glow of a comet is not from collisions but from light itself, from photons exchanging energy with atoms in a delicate quantum dance. Both auroras and comet glows are manifestations of light and matter interacting, creating beauty in different ways. Stories give meaning to events. Humans are storytelling creatures, making sense of the world through narratives. Science itself is a kind of storytelling, constructing narratives that explain observations. The story of 3I Atlas is one of wandering, chance, and discovery. It wandered through space for eons, encountered our solar system by chance, and was discovered by humans who looked at just the right place at the right time. This story connects us to the larger universe, reminding us that we're part of a cosmos that is vast, ancient, and full of surprises. In telling the story of the comet, we're also telling a story about ourselves, our curiosity, our desire to understand, our capacity for wonder. As 3I Atlas moves away from the sun and fades from view, it joins the countless other objects we can no longer see. Space is vast, and most things in it are invisible to us. We see only the tiniest fraction of what exists. Yet, even unseen, these objects are there, moving through their trajectories, following the laws of physics, silently being. The comet will continue its journey, watched or unwatched, known or unknown. Its existence doesn't depend on our observation. This is both humbling and comforting. The universe continues regardless of us. We are observers, participants in a reality much larger than ourselves. The final observations of 3I Atlas will happen sometime in 2026 or 2027, when it becomes too faint, even for the largest telescopes to detect. At that point, it will slip beyond the threshold of human perception, returning to anonymity. But the data gathered during its brief visibility will remain. Thousands of images, hundreds of spectra, terabytes of data archived in databases accessible to future scientists. Long after the comet itself has faded, researchers will study these records, extracting new insights as analysis techniques improve. In that sense, the comet's visit never truly ends. It leaves a permanent mark in our scientific record, a gift of knowledge from the stars. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Comets orbit stars. Stars orbit galaxies. Galaxies move through the universe. All are circles, cycles, endless orbits. Like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits. Unhurried, unresisting, simply existing. We're almost there now. Distance is a kind of time. The farther away something is, the longer ago we see it. Light from the nearest star takes 4 years to reach us. Light from distant galaxies takes billions of years. In this way, looking outward is looking backward. When we observed 3I Atlas, we saw it as it was minutes ago, the light travel time across space. This means the present is always slightly out of reach. We live in a bubble of delayed information, seeing the past presented as now. It's a strange feature of living in a universe where light is fast, but space is vast. Water is common in the universe. It forms wherever hydrogen and oxygen exist together at the right temperatures. Comets contain water ice. Moons in the outer solar system have subsurface oceans. Even interstellar clouds contain water molecules. The detection of water in 3I Atlas was not surprising in itself, but it was confirmation, a check mark indicating this distant object formed under conditions similar to our own system. Water connects us across the cosmos. The word asteroid means star, because early observers thought asteroids looked like stars through their telescopes, points of light rather than extended disks. The word comet means hairy, describing the flowing tails. These names reflect how things appear, not what they are. Appearances can mislead. What matters is understanding, not first impressions. Science looks beyond appearances to discover the underlying truth. Meteors are brief. A meteoroid, a grain of dust or small rock, enters Earth's atmosphere at high speed. Friction with air heats it white hot, creating a streak of light lasting seconds or less. Then, it's gone, vaporized or fallen to the ground. But, in those brief seconds, it creates beauty. Fleeting moments can be intense and meaningful. The passage of 3I Atlas is like a meteor on a cosmic scale, brief, bright, then gone. Darkness in space is not empty. It's filled with faint light from distant galaxies, stars too far to see individually, and the cosmic microwave background. Even in the darkest regions, far from any star, there's a gentle glow. Darkness is relative. True darkness may not exist anywhere in the universe. There's always something, some faint light, some trace of energy, marking the presence of reality. The future is uncertain. We can calculate trajectories, predict positions, estimate probabilities. But chaos theory tells us that small uncertainties grow over time. Three-body problems have no perfect solutions. Long-term predictions become unreliable. Yet this uncertainty is not a failure. It's a feature of the universe, allowing for surprise, for the unexpected, for freedom within the laws of physics. 3I Atlas's distant future is uncertain. And that's okay. Mountains on Earth form when tectonic plates collide, crumpling rock upward. Mountains on comets, if they exist, form differently, perhaps from ice cliffs exposing layered strata, or from ridges left as surrounding material sublimates away. We don't know if 3I Atlas has mountains. Its surface remains a mystery, but imagining it is enough. Imagination bridges the gap between what we see and what might be. Ice can take many forms. On Earth, we're familiar with ordinary ice, known scientifically as Ice 1H. But under different pressures and temperatures, water freezes into other crystal structures. Ice 2, Ice 3, all the way to Ice 18 discovered recently. Comets contain ordinary ice and also more exotic forms, mixed with other frozen gases. This diversity of ice reflects the diversity of conditions in the universe. Organic molecules, those containing carbon, are found throughout the universe. They form in interstellar clouds, around dying stars, in planetary atmospheres. They're delivered to planets by comets and asteroids. These molecules are complex, sometimes hundreds of atoms arranged in intricate structures. They're the building blocks of life as we know it. Whether 3I Atlas contains organic molecules, we don't know for certain. But likely it does. Life's ingredients are scattered widely across the cosmos. Humans evolved in a world of sound. Rustling leaves, flowing water, voices of others. These sounds shaped our nervous systems, our sense of safety and danger. But space offers something our ancestors never experienced: perfect quiet. Without sound to orient by, other senses become more prominent. Vision dominates. Internal sensations grow louder: heartbeat, breath, the subtle movements of your own body. This sensory shift might explain why space imagery helps some people sleep. It takes us out of our evolved acoustic environment, creating a kind of sensory reset, a quiet canvas for the mind to project whatever it needs. Every culture has myths about the sky. The ancient Greeks saw heroes and monsters in the constellations. Chinese astronomers tracked comets and planets with precision. Indigenous peoples of the Americas incorporated celestial events into their calendars and stories. These myths connect us to our ancestors, showing that wonder is universal. When we study 3I Atlas, we're continuing that tradition, adding our chapter to the human story of sky watching. The coldness of space is profound. Without an atmosphere to hold heat, temperatures drop toward absolute zero. At that temperature, motion nearly stops. Molecules vibrate minimally. But even in the cold, change happens. Radioactive decay continues. Cosmic rays bombard surfaces. Chemical reactions, though slow, proceed. Cold doesn't mean dead. It means patience, waiting, preservation. 3I Atlas preserved its ancient chemistry in the cosmic cold for billions of years. Reflections on water surfaces show the sky. In still lakes, mountains and clouds mirror perfectly. This symmetry is calming. The universe also has symmetries, physical laws that don't change over time, conservation principles that hold universally. These symmetries give structure to reality. They allow us to predict and understand. In symmetry, there's beauty and reassurance. The laws that govern 3I Atlas are the same laws that govern us. The speed of light is a cosmic speed limit. Nothing with mass can reach or exceed it. This limit shapes the universe, determining causality, defining how information can spread. It means distant events affect us only after a delay. It means we're isolated in time as well as space. But this limit also connects us. Light from 3I Atlas traveled to us at this maximum speed, carrying information as fast as physics allows. Sand dunes on Earth shift gradually, moved by wind. Dunes exist on Mars too, shaped by thin atmosphere. Even Titan, Saturn's largest moon, has dunes made of hydrocarbon particles. Shifting landscapes are common in the universe. Change is constant, though often slow. 3I Atlas also changes, losing mass, altering shape, transforming as it ages. Nothing is permanent. Everything flows. Fractals are patterns that repeat at different scales. Trees branch, rivers fork, coastlines zigzag, all showing fractal properties. Cometary surfaces may also be fractal, rough at every scale, from kilometers down to microns. This roughness affects how light reflects, how heat conducts, how ice sublimates. Complexity at small scales influences large-scale behavior. The universe is intricate, layered, endlessly detailed. Music and mathematics connect through pattern and ratio. Musical scales, harmonies, rhythms, all involve numbers and relationships. The orbits of planets also follow mathematical patterns. Resonances, where orbital periods form simple ratios. There's a harmony in the heavens, a celestial music we hear not with ears but with minds. 3. Atlas moves to this silent music, following the gravitational symphony of the cosmos. Horizons define the edge of what we can see. On Earth, the horizon is where sky meets ground or sea. In space, light travel time creates horizons. The observable universe extends only as far as light has traveled since the Big Bang. Beyond that horizon, space may continue infinitely, but we can't see it. 3. Atlas came from beyond our horizon of knowledge, appearing suddenly, a surprise from the unseen reaches. Rain falls when cloud droplets grow heavy enough to overcome air resistance. Each droplet's path is shaped by air currents, turbulence, randomness. Millions of droplets falling together create the experience of rain. Similarly, the motion of 3I Atlas is one trajectory among countless interstellar objects, each following its own path. Individually unique, collectively they form patterns, populations, statistical distributions. Understanding one helps understand all. The moon reflects sunlight, glowing softly in our night sky. Without the sun, the moon would be invisible. Comets also shine by reflected and re-emitted light, not from their own energy. They're secondary lights, borrowers of radiance. Yet this borrowed light is real and beautiful. In a way, we too shine with borrowed light, made from materials forged in stars, carrying forward the legacy of cosmic processes that came before us. Waves on water surfaces carry energy, rippling outward from disturbances. Light is also a wave, an electromagnetic oscillation carrying energy through space. Both can interfere, creating patterns of reinforcement and cancellation. Understanding waves helped us understand light, and light helps us understand the universe. 3I Atlas sent waves of light toward us, ripples in the electromagnetic field, carrying the news of its existence. Footprints in sand or snow mark where we've been, but wind and weather erase them quickly. In space, there are no footprints. Trajectories leave no visible trace. A comet passes and space closes behind it, unchanged. We know it was there only because we observed it. Memory and records preserve what would otherwise vanish. Our documentation of 3I Atlas is its footprint, lasting longer than the comet's brief visibility. Clouds form when air rises, cools, and water vapor condenses into droplets. The same principle, cooling causing phase changes, drives comet activity, but with different substances. Rising temperature causes phase changes from solid to gas. Opposite processes, same physics. The universe uses the same rules everywhere, just applied to different materials and conditions. There's unity in diversity. Twilight is the transition between day and night, when the sky glows softly though the sun is below the horizon. It's a liminal time, neither fully light nor dark. Observing 3I Atlas was also a kind of twilight experience. It appeared briefly in our awareness, transitioning through our solar system, then fading back into the dark. We caught it in passage, in that transitional moment, before it returned to night. Gratitude is a response to gifts received. The universe gave us 3I Atlas, a visitor from afar, carrying information about distant places and ancient times. It gave us the chance to observe, to learn, to wonder. For this gift, freely given by the random motions of matter and gravity, we can feel gratitude, not to a giver, but to existence itself, for being here, aware, able to witness and understand. For this moment, this breath, this awareness, thank you, universe. Thank you, 3I Atlas. Thank you for wandering close enough to be seen. And so, our quiet journey through the story of 3I Atlas comes to a gentle close. We've traveled from that first detection on a summer night in Chile, through months of observation and discovery, to the perihelion passage when the comet felt the sun's warmth for a brief moment, and now outward toward its eventual return to the cold, dark between stars. From one faint point of light in a telescope to a rich story of chemistry, motion, and cosmic connection, we've glimpsed how interstellar space is both vast and intimate, holding wanderers like this ancient comet that crosses paths with our small world purely by chance. 3I Atlas reminds us that our solar system is not isolated. We're part of a galactic neighborhood where objects drift between stars, carrying samples from one system to another. Much of the universe's activity happens in silence, in darkness, in places we cannot see directly. The comet teaches patience, reminding us that understanding takes time, observation, and careful thought. Without visitors like 3I Atlas, we might forget that the space between stars is not empty, but full of travelers. By pausing to notice this small, icy wanderer, we glimpse the extraordinary in the ordinary motion of gravity and light. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about consciousness itself. Yours, mine, everyone listening, all awareness everywhere, perhaps all connected in ways we don't yet understand. You are not alone in the universe of minds. Let your entire being dissolve into the ocean of consciousness, into dreamless rest, into the space before thought. Prepare for deep sleep. No boundaries left, only peace. If this thoughtful exploration of an interstellar visitor made you feel less alone, whisper it forward to someone awake tonight. It may bring comfort to one more wandering consciousness. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. Allow these thoughts of comets and stars to fade now, like distant lights seen through closing eyelids, leaving only the peaceful calm behind. Feel your breathing deepen. Notice your body feeling heavier, as if gravity itself is gently pulling you down into rest, into the soft support beneath you. If sleep comes, Let it carry you like a comet drifting through space, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, 3I Atlas will still be moving through space. The stars will still shine. The universe will still turn. But tonight belongs to stillness. Rest well, fellow traveler. And remember, we are all made of stars, watching stars, drifting through space together on this small blue world. Good night.